Good evening, everyone. So we're doing Stokes' theorem today. Stokes' theorem is really interesting. It's the one theorem we do at the end of chapter 16 because Stokes connects line integral with surface integral. And it's actually the curl of f. So when we're talking about this surface integral here. So he connects a line integral with a surface integral, which is really interesting. Where can this be useful? Recall Green's theorem? Green's theorem was pretty cool, right? And it dealt with a closed path, but it was limited because it was only in the two-dimensional space. Do you recall that? So while you're copying, I just want to point out, like, Green's theorem, what an awesome theorem it is. Yeah, but it was for, like we just did, D, remember it's like P and Q. The derivative Q with respect to X minus derivative Q. This was only for, as you can tell, P and Q, right? A vector field with these two components. So what's great about Stokes is, there you go. We're talking about, what about in three-dimensional space? If you got something that can maybe make it easier to evaluate a line integral, when the path is in three-dimensional space. You got a path that maybe goes over here, comes up here, goes down here three-dimensionally, not just in a two-dimensional plane, and it's Stokes' theorem. So it looks weird, but it actually can make it a lot easier to work a line integral, especially if you had to work three line integrals just to get the answer. So that's what Stokes' theorem is all about. I do want to point, they say positive orientation, so now you're like, what does positive orientation mean in three-dimensional space? That would mean moving counterclockwise as viewed from above. So if I look down like on the XY plane, if I move down, look down on the XY plane like this, then we'd say, okay, moving counterclockwise, that would have positive orientation. Positive orientation for that. Or here's another thing, if you walk in the positive direction around the curve and your head's pointing in the direction of the normal vector, so positive orientation. I'm moving in a positive direction, and my head points in the direction of the normal vectors off the surface. Because remember when we talked about a normal vector, I'll point right here. That's a normal vector. So if I walk in a positive direction, and my head points in the direction of the normal vector, then my surface should always be to the left of me. That's how you know you got the positive orientation. I just want to say that as well. That's actually the author's statement at the beginning of section 16.8. He makes that statement. Because it's kind of weird. You're like, we got a surface integral going on and a line integral. Now I want to be clear about one thing. We're going to do a few problems today. When they say use Stokes' theorem to evaluate a line integral or a surface integral, they want you to use the theorem. So if we just ignored this use Stokes' theorem part, you and I would just start working a line integral, wouldn't it? Isn't that a line integral? So if they say use the theorem, they want you to use the theorem. Sometimes that's the one thing that gets lost. Students just, they see this and they start working a line integral. They want you to use the theorem. So what that means is, we'll keep this simple. If they say use Stokes' theorem to do this, they want you to do the other side of that equal sign. This is Stokes' theorem. They want you to work it this way. They want you to attack the problem by this. Okay? So if they said use Stokes' theorem to evaluate this, then we'll work a line integral. We'll work a line integral like we did back in section 16.2. Way before 16.8. So in this particular problem, they said use Stokes' theorem to evaluate this, and that's our focus. So I want to point that out. Like, how are we going to attack this problem to begin with? It's recommended that we attack it this way. It should be easier. That's another way of saying it. You may argue, well, I can do it on either side of the problem. I can do it this way or this way to work the problem. It should be easier to do it this way. That's how we're going to attack the problem, by doing this. All right, so this is what you and I are going to do. The curl of the vector field, but we've got a little work to do, but it still should be a lot easier than doing the line integral directly. So can we draw a picture of this? Everyone, there's a triangle. It's got these vertices. Can we just draw a picture of that? What does that look like? All right, y-axis, z-axis, x-axis, 1, 2, 3, 1, 2, 3, 1, 2, 3. There is the surface that you're talking about. That's the surface right there. It's a plane. And that's a plane right there. Use Stokes' theorem to evaluate the line integral, where there's the vector field. C is the triangle with these vertices oriented clockwise as viewed from above. So which way would the path be if we were doing a line integral? If we look at this from above, like downward,
It's going to
move counterclockwise, wouldn't that be, because that means with the pointing clockwise as viewed, is it clockwise or counterclockwise? Let me look. Oriented, and I apologize everyone, can I change that word? It was counterclockwise. If it was clockwise, it would have gone the other way. It's counterclockwise. Ooh. I'm glad I caught that. It wouldn't have been a big deal, we would just got a negative answer to the problem. Oriented counterclockwise as viewed from above. That's for positive orientation. That's the positive orientation. Alright, so now, doesn't that mean this is the path we're taking? So in other words, we're saying, compute the line integral, where maybe you start right at that point. You're going to go along this line right here, then go up that line, and then come back this line. That's what we're trying to do. Compute the line integral. Well, if we did this in section 16.2, then we have 3 line integrals to compute, right? And that's a pretty intense vector field there. That could be a lot of work. A lot of work. That could be over 2 pages of work just to get that final answer. Whereas this is going to give us the answer in one shot. So we'll attack it this way. So the biggest challenge here, I'm going to rewrite this. We go, what is curl of f dot this ds equal to? It's equal to all this. So I'm going to write that. But are you okay, everyone? If this is our surface, can't we project this onto the xy plane? And that's what I'll do. So I'm going to use x's and y's here. So I'm going to write this is equal to that region D. I need to point to where D is in that image. I'm going to do f composed of r of x and y dot the normal vector rx cross ry dA. Got a little dA there though, at the end. This is the normal vector. So we got to make sure that normal vector is pointed upward. That's what I mean. We got to make sure the normal vector is pointed upward. Because could you imagine if I walked along this path here? If I walked along this, wouldn't my head point in the same direction as the normal vector? That's what I'm saying. So we'll make sure the normal vector is pointed upward when we do that. Okay, so this isn't going to be bad, everyone. This D they're talking about, if we project it onto the xy plane, that D is this part right here. We're going to project it right onto the xy plane. That's our projection. So, here's the biggest challenge by far. That R, the surface. They didn't give us the surface equation. I need it. We need it. How do I parameterize that surface? And that's what's tricky. You're like, it's just a plane, isn't it? So when I want to make sure it's going to be pretty simple. We didn't have to do something from chapter 12. Do you agree the equation of this plane? I need that first. That the equation of this plane, they didn't give it to us. All they did was say move through these points. But do you agree the equation of the plane is this simple equation? X plus y plus z equals 3.
Mm-hmm.
Can you examine that? And I want to be clear, that they did that on purpose, the problem out of the book. If they gave you some bizarre, 5, 2, 7, then you and I would have had gone back to our knowledge that we know that how we can get the equation of a plane, where, I got to get a normal vector to the plane, and I need a point in a plane, and we'd have to do a cross product. It'd probably be about 5 to 10 more minutes of math just to get that. But we did that back in chapter 12. I believe the author's doing this on purpose to give you very simple points so it's real easy to create the equation of a plane. Okay? So I think I have your problem practice set. I think I have one similar to this with 2, 0, 0, 0, 2, 0, 0, 0, 2, what would be the equation at that point? If that was a 2, and that was a 2, and that was a 2, it would be what? X plus y plus z equals 2. It's really just to keep this problem a little bit short. Don't have us working for 20 minutes on it, right? Because that would take a lot longer just to get the equation at plane if you just had these 3 random points. We'd have to go get the vectors and get the normal vectors. So, can you help me parameterize that? That's the hardest part. Now that we know that, is that plane right there, that triangle, what's a parameterization of this? What's R of x and y? You want to let x equals x? Y equals y? And what's this third component?
X minus y. 3 minus x minus y.
Way to go. 3 minus x minus y. I parameterized the plane. So how about, let's get that normal vector first. Let's do this first right here. We're going to need it. So let's go find that normal vector. Although there might be someone in here who already knows what it is. That's okay. Let's go through the motions. We know how to do it. Rx cross Ry, right? All right. What's a partial of R with respect to x? Goes fast. 1, 0, and. That's why I want to do it with you. It's pretty easy to do. 1, 0, negative 1. What's Ry? What's the partial with respect to y? 0, 1, and?
Negative 1.
Now, this is going to be interesting. When we get this, we're going to make a connection with stuff we've done previously in this course. What's Rx cross Ry? What's the cross product of those two partial derivatives? What do y'all get for the first component?
1, the
Work
first
that
one.
out. That times that minus that times that.
1.
Remember the middle component, you got to change the sign. Negative. This times this minus this times this. Negative, negative 1 is?
Positive.
Negative, negative 1 becomes?
Positive.
Positive 1. And then how about the last component?
0.
1 times 1 minus 0 times 0?
Yeah.
1 times 1 minus 0 times 0?
1.
Are you kidding me? And I think you'll make the connection. Oh yeah, that's the normal vector. Do you remember back in chapter 12, the coefficients to the x, y, and z represents the what?
Normal.
The normal vector of the plane, I know. So we're like, aha, right? Aha, yeah. The 1, 1, 1, that's what we should get. And is it pointed upward? Because we got to make sure it's pointed upward. Because they said we've got the counterclockwise as viewed from above, so we want to have positive orientation. That's where they say positive orientation. Then we got to make sure the normal vector is pointed up, which we do. Cool. By the way, do you remember I accidentally had clockwise up here? All we could have easily done is just used Ry cross Rx. It would have made the answer negative. That's the only difference. I thought we'd keep it with positive orientation. All right, so we got this. This is what I mean. This problem's not going to be hard. Because that's 1, 1, 1. This is way better than doing 3 line integrals. So this is going to be 1, 1, 1. Okay, so I'm going to set this up. I'm going to get the curl of f of R of x1. And do the dot product with this nice little what? And we'll project it right over that yellow region. But, now what do we got to do? We got to find the curl. So do you remember how to get the curl? So now I got to find the curl. So like, okay, what's the curl going to be? We did all this. We parameterized the plane. What's the curl? The curl of f is, then we can work out this double integral. Del cross it. We haven't done the curl since section 16.5. Let's try it. We can make a matrix, ijk, ddx, ddy, ddz, and I gotta put all that here, all that here, and all that here. So maybe I'll write it like on top of each other. Will that work? Okay, I'm gonna do that here. Right here, I'll just write 2x squared plus 2y squared. I'll write it vertically. The second component is 2y squared plus 2z squared. And this one is 2z squared plus 2x squared. I'll just extend these. That's all I'll do, just to squeeze it in there. Because I mean, we gotta do a cross product. So wipe out the first column. What's the derivative of that with respect to y? Minus the derivative of that with respect to z. So here comes the curl. Curl of f is, let's see what we get. That times that minus that times that. Well, derivative of that with respect to y is, do y'all get 0? Well, what's the derivative of that with respect to z? Minus 4z? I want to make sure everyone gets the same thing. That's my first component. You'll get minus 4c? Nice. Hey, middle component, we got to do what? Change the sign. All right, we'll wipe out this. Now do the derivative of that with respect to x minus derivative of that with respect to z. I get negative 4x minus 0. And for the last component, wipe this out. Derivative of this with respect to x minus derivative of that with respect to y. And I get minus 0 minus 4y. Ah, there's the curl. But double check it. Everyone see how I did this? Sorry I had to squeeze everything in there. I just want to make sure. I'm like, that was a lot. I got it all in there. We've got the curl of the vector field F. Now, I'm going to put that here. And we still got enough room to compute this. I'm going to put that here, but we're going to have to substitute something for the z because everything's going to be dx dy or dy dx, right? And we're not going polar, are we? Look at that. See that? That's our reach. We're going to keep it. We're going to keep it Cartesian. So now I'm going to just take this problem and say, all right, now we got this right here, and it's equal to double integral negative 4z negative 4x negative